Okay, number 11. A town's population has been increased at a constant rate. In 2010, the population was 46,020. By 2012, the population had increased to 52,070. Assuming this trend continues, predict the population in, or assume this trend continues, predict the population in 2016. Okay, so we can do this like we did number 9. We have 2 points, 2010, and the population then was 46,020. And we have the point 2012, and the population at that time was 52,070. Alright. So again, use the 2-point equation for a line. Y minus y1 equals y2 minus y1 over x2 minus x1 times the quantity x minus x1. Alright. So we've got y minus 46,020 equals 52,070 minus 46,020 all over 2012 minus 2010. Oops, not 21, 2010. There we go. And then x minus 2010. Right at the end there, in parentheses. So just focus on the right hand side of the equation. We've got, do the arithmetic, 60/50 over 2. Times the quantity x minus 2010. 2 goes into that evenly. That's 3025 times the quantity x minus 2010. So distribute that through. You've got 3025x minus, this times minus 2010 is minus 6,080,250. All right. And then add 46,020 to both sides and you get y equals 3,025x minus 6,034,230. All right. Now the population in 2016, plug in 2016 right there. Y of 2016 is what we want. 3025 times 2016 minus 6,034,230. Do the arithmetic, and you will get 64,170. All right. So there we go. Okay, here we go with number 13. For the following exercises, consider this scenario. A town has an initial population of 75,000. It grows at a constant rate of 2,500 per year for 5 years. So 13 says, find the linear function that models the town's population P as a function of the year T, where T is the number of years since the model began. Alright, so it's going to be a linear function because it's a constant rate of growth, 2,500 per year over that 5-year time span. So that basically is the slope of the straight line. Alright, so what's the initial value? P of 0. That's the starting point, and T is the number of years since the model began, so 0 would be right when the model starts. Alright, so the starting point, or the starting population, was 75,000, which they told us. That's the initial value. Alright, so that's you can call it the p-intercept, or if you're using a y-axis, the y-intercept. And the slope is 2,500, alright? That's the rate of growth per year, 2,500 per year. So the function then, it's pretty easy. This is the y-intercept, that's the slope. Slope-intercept equation, right? So P of t is our function, and that's equal to 2,500 t. I'm using t's instead of x's here. Normally we'd use an x, but we put a t there. Plus 75,000, or following the format y equals mx plus b, right? Alright, 75,000, which is our y or p-intercept. And we could put a domain restriction on this. The domain are what are allowed for t's. So we can go from 0 to 5, including 0 and 5. Because this model is only valid up to 5 years from the start, from the initial value. That's what the problem states. 2,500 per year for 5 years. We don't know what happens beyond that. They don't tell us. All right. So that's our answer. Now the book doesn't give you this domain restriction, but I thought I'd throw that in because that would be valid. All right, and that would be important, really. Number 15. If the function p is graphed, find and interpret the x and y intercepts, or you could call them the t and p intercepts, respectively. So let's find the t-intercept or the x-intercept. I'll call it t. Alright, so we want to solve p of t equals 0. Where does the graph intersect the x-axis or the t-axis? So what we do is we set the function 2,500 t plus 75,000. Set that equal to 0. And then we solve for t. So subtract 75,000 from both sides, and then divide both sides by 2,500, and you get t equals negative 30. Alright, so we have the t-intercept is negative 30 and 0. So it could mean that 30 years before the model started, there was no population. But actually that is outside of the domain of the model. The model they gave us only goes from 0 to 5. So that's just speculation on our part, right? We really don't know the meaning of that, right? It may have no validity for this model. It depends on what they're using it for. So it may not continue in a straight line. It may be just a straight line in just that little short time interval from 0 to 5 years, all right? So if this was real life, you really couldn't say for sure. Okay, so let's take a look at the p-intercept, or the y-intercept. So that's p of 0. So that's 2,500 times 0 plus 75,000, which is 75,000. So that's the town's initial population for this model. Number 17. When will the output reach, the book says reached, I should say reach, 100,000. So you set P of t equal to 100,000 and solve for t. Alright, P of t equals 100,000. So that's 2,500 t plus 75,000 equals 100,000. And so now we get 2,500 t, subtract 75,000 for both sides, that equals 25,000. And so t equals 10. Divide both sides by 2,500. Alright, so 10 years after the beginning of the model is what that means. But again, this is outside of the model's domain, which was given to us as 5 years. Alright, this model is valid for 5 years, so if it continues and it's in that trend, then in 10 years the population will be 100,000. Okay, number 19. For the following exercises, consider this scenario. The weight of a newborn is 7.5 pounds. The baby gained a ½ pound a month for its first year. Okay, so the question for 19, find the linear function that models the baby's weight W as a function of the age of the baby in months, T. So the initial value is 7.5. In other words, W of 0, when the model starts, the weight is 7.5 pounds. Okay, and the slope is given to us as baby gained a ½ pound a month for its first year, so 0.5, 1/2. Alright, so again, use the point slope equation, or the slope intercept rather equation. This would be your W intercept, and that would be your slope m. Alright, so W of t is equal to 0.5 t plus 7.5. And we can't give a domain restriction 0 to 12 inclusive. Where 12, that's 12 months or 1 year. Alright, so again, the domain is not in the book's answer. Alright, but it does have a restricted domain because of the statement of the question or the problem. Alright, for its first year, these were the growth conditions of the baby. That's what it told us for the first year. So anything outside of that time frame isn't really valid. Alright, if you can't really continue to use this same model in real life, because we really don't know this particular baby, how it grew afterwards, after the first year. So, and of course before it started, before 0, well, you know, the baby wasn't born yet. So, there you go. Number 21. If the function W is graphed, find and interpret the x and y or t and w intercepts. Okay, so let's find the t intercept and then the w intercept. So the t intercept, we set w of t equal to 0 and then solve for t. Alright, so 0.5 t plus 7.5 equals 0. And then 0.5 t equals negative 7.5. So just subtract 7.5 from both sides, divide both sides by 0.5, so you get t equals negative 15. So this implies that the baby's weight was 0 15 months before birth, which is really absurd, right? So, well, yeah. I mean, it takes 9 months to initiate and grow a baby. So 15 months before it was born, it wasn't even conceived yet. All right. Well, you could say it was 0 if you want to consider it as a baby that doesn't exist. All right. So not yet. The baby didn't exist yet, so it had a weight of 0. Okay, that kind of makes sense. And then there's the W-intercept. So that's W of 0. That's the initial value, which we already know, right? That's you don't really need to do all this computation. What was the baby's starting weight? And we can just take that from the statement of the problem itself, or you can plug it in, plug or t equals 0, and you will get the starting weight of 7.5 pounds. All right? So the baby's weight was 7.5 pounds at birth. Okay, number 23. When did the baby weigh? The book says weight. When did the baby weight? No, it should be weigh. 10.4 pounds. Okay, so you set the function equal to 10.4 and then solve for t. Alright, so you've got W of t is equal to 10.4. So W of t is 0.5t plus 7.5 equals 10.4. Subtract 7.5 from both sides. 0.5t equals 2.9. And then you divide both sides by 0.5. So t is equal to 5.8. Okay. So when the, again, this is in months, t is in months, so when the baby is 5.8 months old, the baby weighs 10.4 pounds. Number 25. For the following exercises, consider this scenario. The number of people afflicted with the common cold in the winter months steadily decreased. Steadily decreased. All right, that means in a constant manner. All right, steadily. So you know it's going to be a straight line. By 205 each year from 2005 until 2010. In 2005, 12,025 people were afflicted, so that's your initial value there in 2005. And we know the slope. Alright, so the slope will be negative 205 because it's a decreasing function. So 25 asks, find the linear function that models the number of people afflicted. Now the book says inflicted, and it really should be afflicted, A-F-F-L-I-C-T-E-D, okay, with the common cold, C, capital C, as a function of the year T. All right, so again, the slope, or the initial value is C of 0. That's our y-intercept, or our c-intercept. And that's 12,025. The slope is negative because it's decreasing, negative 205. All right. So C of t then is negative 205t plus 12,025. Again, we can put the domain restriction 0 less than or equal to t is less than or equal to 5. All right, that's the model is the model is valid for this time frame. All right, where t is number of years after 2005. Alright, so the book does not specify in its answer the domain restriction, and it doesn't elaborate on what t means here. Alright, so again, t is the number of years after 2005. Okay. Number 27. If the function c is graphed, find and interpret the x and y, or the t and c respectively, intercepts. Alright, so we've got the t-intercept first. That's usually the harder one to calculate, so we'll do that first. Get the hard stuff out of the way first while you have the energy, and then you can tackle the easy stuff when you're tired, right? Okay, so c of t, set that equal to 0, solve for t. So you've got negative 205t plus 12,025 equal to 0, and then subtract 12,025 from both sides. So you get negative 205t equals negative 12,025. Divide both sides by negative 205. You can get a decimal approximation on this, about 58.66 for t. Alright. Now that implies that in the year, again, these t's represent number of years after 2005. So this is about almost 59 years after 2005. That would be in the year 2063. In year 2063, all right, there would be no one afflicted with the common cold. There will be no one afflicted with the common cold. It will no longer be common, right? Because there will be nothing there. No more colds. Alright. Hope it's before that time. The c-intercept. That's the initial value of c of 0. And we already knew that, but you can do the computation with the function. Everything is consistent in mathematics, and there's often more than one way to do something. Which brings up a nice point. You should know these alternate ways. You shouldn't just look at that and, oh, I already know it's 12,025. Why bother with all this? Well, you should know that there are alternative ways, and in mathematics, that will often help you to solve a problem when you get stuck. All right, think of an alternative way to do it, and it may be much easier that way. All right, granted, in this problem that's not the case, but just be aware that there are alternatives, and mathematics is consistent throughout. So you can use many various different ways, even from other fields of mathematics, to solve a problem. Okay, so even if it seems like more of a difficult way, it may get you out of a rut. Okay, I've done that myself many times. So it's good to know the alternatives. So even doing it this way, it's good to know that you can do it this way. Alright, so that means that in 2005, 12,025 people were afflicted with common cold. Okay, 29. When will the output reach 0? Well, we already know that. That's from exercise number 27. All right, that's our T-intercept. Okay, so what year was that? Well, T we found was 58.66. So 58.66 years after the start of the model, which was in 2005, the output will be 0. All right, so you add 2005 plus 58.66 and you get about 2063. Okay, so we already came to that conclusion in exercise 27. So we're ahead of the game. Okay, number 31. For the following exercises, use the graph in figure 7, which shows the profit Y in thousands of dollars of a company on a given or in a given year T, where T represents the number of years since 1980. So here's figure 7 for you right there. Okay, so 31. Find the linear function y, where y depends on t, the number of years since 1980. Okay, so here's how we do it. We have 2 points that we can see from the graph, and you can see where I've pointed these out. Right, we've got that point, and we've got that point. Okay, that's where t equals 20, y is 140, where t is 25, y is 130, right? So you got 130 and 140, all right? So you can use those 2 points. You can use any 2 points on that line. They seemed easy to me to use. It doesn't matter which 2 you use. All right, pick ones that you can see the exact integer values for, right? So make yourself or make it easy for yourself. So we have 2 points, and then we can use the 2-point equation for a line to get the function. So we've got 20, 140, and we have 25, 130. Okay, so the 2-point equation for a line, that's basically the point slope equation, but with slope we use the actual slope formula. So y minus y1 equals m times the quantity x minus x1, or in this case it's going to be t minus t1. What's m? It's y2 minus y1 over, we're using t's now, t2 minus t1 times the quantity t minus t1. Alright, so here's t1, y1, t2, y2. Alright, so we've got y minus 140 is equal to 130 minus 140 over 25 minus 20 times the quantity t minus 20. Alright, just focus on the right side of the equation. We've got negative 10 over 5 times the quantity t minus 20, and reducing that to negative 2, we get negative 2 times the quantity t minus 20. Then we distribute the negative 2 through, we get negative 2t plus rather. Negative times negative is positive. Remember, that's 40. There we go. And now we can add 140 to both sides of these two equations, and you get y as a function of t. I'll just write y of t. You can just write y if you want to. It's really a function of t. Y of t equals negative 2t plus 180. All right. So there's the answer to that one.